So good evening, everyone. Okay, so in first part, I have introduced how to do the readable refinement using GSAS2 software, and I have shown an example with perovskite oxide. Last time, two queries were are there, one by Samarth, I think, that is about the goodness of fate. Okay, so what is the ideal value of goodness of fate? Okay, or the best value when your simulated line is matching with the experimental line, means when you are achieving the global minima, what will be the ideal value of goodness of fit? Yes, it is 1, because it is the ratio between residual weight profile and the expected residual. Expected residual is calculated value by your system. Okay, the software uh, before doing the refinement, software only can calculate the expected profile residual, which so we have to maximize our or minimize the RWP, which will be minimized by successive simulation or iteration cycles. Okay, so our goal is to reach RWP to the R expected. Okay, so this value should be the ratio, uh, this value should be 1 at ideal case. Okay, so it is not 0. So at ideal situation, goodness of fit is the 1. Okay, and next question was from Aniruddha. So it is about whether we can do the Rietveld refinement for the amorphous sample. Okay, so here is an example for of an amorphous or highly polycrystalline sample. So it is suggested that for highly polycrystalline sample, one should not do the background correction. Okay, because background bears lots of information, and since we have broad peaks during highly polycrystalline sample, so we should avoid the background correction. Okay, without background correction, one can do the refinement. So these two questions uh, were there, and today I'll be presenting the next part of the Rietveld refinement, where we're using a more complicated system, and this system we have actually we have worked on, and we have published in our Angio paper. You can see there we have worked with heteroalloy. Okay, so we have worked with nickel silver alloy material, and if you see our XRD of the nickel silver alloy, where nickel concentration is 0.95 and silver concentration is 0.05. Okay, making a full extent of 1. Okay, so it is showing XRD peaks here. Uh, means this is the XRD pattern of the alloy. So if you see the individual XRD of silver and nickel, these alloy peaks are actually matching with the individual silver and nickel peaks. So one can misunderstood, or from apparent thought, one can say that it is a heterogeneous alloy, because there is silver peak, there is nickel peak, there is nickel peak, silver peak, and nickel peak and silver peak. So this is from apparent look, it is a heterogeneous alloy. But from TM analysis and from TM, basically from TM elemental analysis, we have found that in a single particle or single nanocrystal, there is coexistence of silver and nickel. So that only can be possible when both are in a alloy form. Okay, so we were confused whether this is a alloy or a heterogeneous mixture. Okay, from TM analysis we found that this is alloy, but from XRD and from basic concept of XRD, we can we can apparently say that it is a heterogeneous mixture. So we are confused. So this is the actual there's a particular example where Rietveld analysis can give can add up huge thing, like the Rietveld refinement first started by Hugo Rietveld basically because of this overlap bit to isolate or to deconvolute the overlap bits. Okay, so after Rietveld refinement, we have found no, there is no heterogeneous phase. There is a complete alloy phase. Like this is for, for glimpse. Like we have found two different alloy phases. One is nickel type of crystal structure, and one is of silver type of crystal structure in terms of the volume of the unit cell. Like see here, nickel type of silver nickel without any alteration in the composition. Okay, composition is fixed, means silver is 95% and sorry, silver is 5% and nickel is 95% in both cases. But see, the volume has changed. So here in the second case, it is taking silver like unit cell, and in first case it is showing nickel like unit cell. Okay, so that we have found from the Rietveld analysis. Along with, we have also found very minimal amount of metallic silver. So for to isolate these things and to deconvolute these things, we need to do the Rietveld refinement. Okay, so now I directly go to the Rietveld refinement part. Oh, so I think I hope you remember the how to incorporate the XML files. So first you have to open the GSAS software. Okay, then you have to import the powder data, which should be in the GSAS dot raw format or any of these format. Okay, and we have converted the Rigaku data to the GSAS raw data using XConvert software. Okay, so now I'm incorporating the data. So
Rahul,
yes.
are you the GSS software? This one is open because the screen is stopped.
Okay, okay. So let me do that. Stop here. Not screen. Is now you can see it.
Yeah.
Okay. So now I'm importing the powder data. Okay. So this is the powder data. Rietveld. So powder data is in raw format. Okay. Dot RW format, and the parameter, as I told you, that it should be in default format. So you have to cancel it. The default window will pop up, and you have to select the default copy K alpha lab data. Yes. So this is the powder XD data. It is now imported. Now you have to import the phase, means the CIF file, standard CIF file. Since we have composition like silver, nickel 95% and silver 5%, so we will take the CIF file for both nickel and silver. Okay, so now I'm taking the nickel CIF file. So this is the nickel. It is now incorporated, and in next, this is the phase. So nickel is incorporated, you can see. Okay, now I am importing the silver phase. Okay, so silver is also imported. uh, Now refine against the nickel only. Let's see whether it is a heterogeneous phase or not. Okay, so I'm checking the refined unit cell for the nickel only. See, silver is empty. I'm not clicking here. Okay, I'm not taking that one. So first you have to do the background correction. So take the Chebyshev functional, and number of coefficient you can increase or keep it as default. Default param coefficient is 3. Okay, so now refine it. With background is refined, and you can look in by using the zooming tool. Okay, so peak is here, so it is not matched because of the different lattice parameter. So you have to refine this lattice parameter. So calculate again, refine again and again, so until you are getting the match in the tooth value. Okay, or you can also manually change this thing, like since the calculated one is coming at 45.45, but experimentally we have found the peak at 44.8. Okay, so you have to do you have to decrease the value of the lattice increase the value of the lattice parameter, or the unit a value. Okay, so I am manually putting it like 3.5. Okay, then defining it. Now check whether it is coming. Yes, it is coming at, it is actually matching with the experimental peak. Now refining once again. Yes, so I think if, this positioning is done, that it is so now the center correction is uh, done by refining the unit cell parameter. Now go to the unit cell, sorry, instrument parameter, where you have to select the copper K alpha source, and you have to refine the zero polarization and this thing. So this is the source refinement. After source refinement, you have to go to Gaussian parameter coefficient refinement, UVW. The RW is decreasing to 10. Okay, and if you see the full X pattern, this this and this peak only get refined, but here there is another peak, there is small peak which are not getting refined. So uh, from here, and we can understand that this XRD is not coming from nickel only, so there must have some other thing. Okay, so one can as I have said, that one can uh, easily tell that it can be a heterogeneous phase. So let take silver in account. Okay, so I'm now clicking the silver refinement cell. Okay, and calculating together. So where is the silver peak is coming? Yeah, it is here. So we have to increase the, where it is? No, silver value is here. So at relatively lower to theta. So we have to decrease the unit cell parameter for the silver. So it is 4.17. Okay, now check. Yeah, it is coming. Further decrease in the unit cell parameter for silver is not actually the what's it, what to say, it is not correct thing, because silver cannot be minimized, the silver unit cell parameter cannot be minimized further. Okay, that is experimentally wrong. Okay, we can do it theoretically, but experimental, that one should not do that. So silver, the ideal value of silver peak, the silver unit cell parameter is 4.17. Okay, so let me refine using 4.17. Okay, oh, and it is falling here. It is actually refining this small peak, the impurity peak. So this peak is not correspond to the silver, and it is also not correspond to the nickel. So it must include both silver and nickel because it is falling in between silver peak and nickel peak. See, nickel peak is here, silver impurity peak is here. So it is in between these two peaks. So it should be, it can be a alloy peak. And where there is a, because this peak is much closer to silver, that means it has silver like unit cell. Okay, but we have silver concentration in the sample is only 5%. So let uh, add some nickel in the silver matrix, okay, by edit atom. So nickel, okay, and take care about the fraction. Silver fraction is 0.05, it's 5%, and nickel fraction is 0.95. But the parameter, unit cell parameter is 4.17, so it corresponds to silver. So we should not keep it manual, so we check the refinement box, okay, here, and calculate it again. Now the peak is coming here, but since the value of A is lower, so that's why it is falling on the silver peak. But as we have incorporated nickel into the silver matrix, so peak should go to higher to theta. Okay, so larger than 4 point, sorry, lower than 4.17. So let's say take it 4.0. What it will happen? It's moving far too much higher to theta. Keep it 4.01 and do the refinement manually. Yeah, it is now falling on the experimental value, but it is it's still at the lower to theta side. So we have to move it to the higher, little bit towards higher to theta. So we have to further reduce the 1 to, let's say, by 0.02 to then refine it. Yeah, I think it is exactly falling here. Yes. So now see, all the peak are now matched with the simulated, means at least the peak position, not the intensity. Intensity we have to refine, but see, all the peak position can be refined using the simulated curves. Okay, so okay, there is the silver impurity still I have to add. So because I have taken the nickel phase and here the silver, it is not silver only, so silver 0.05 and nickel 0.95. Okay, so this is the this phase and nickel. Now nickel, we haven't found any nickel peak because nickel, although nickel is 95%, but here the here this peak uh, giving the unit cell parameter is 3.5, which is uh, lesser, which is more than that of the pure nickel. Okay, so that actually indicates it is not only nickel, instead it is a nickel silver alloy. Okay, so here also you have to incorporate nickel and along with the silver. So append atom, take a silver, coordinates are same, silver concentration will be 0.05 and nickel 0.95. Now refine it. What is happening? Yes, refine it again until it's okay. I think it is saturated now. Uh, but the intensity are not matching, so we have to refine. We have to do the instrument parameter refinement. So go to the instrument parameters and try to refine the first three, that is intensity and the zero correction and polarization correction. Then UVW coefficient correction, then XYG. Okay, but still the intensity is are not matching. That's why the W is weight residual is 15 and goodness of fit is around 11.41. So what we have to do, we have to check the phase fraction. Okay, like the in nickel phase. So let me write it as nickel 0.95 and silver 0.05. So it is nickel, it has nickel type of crystal structure, and this silver one has silver type of crystal structure. But see the phase fraction here, phase fraction is 44% silver type of structure, while nickel type of structure has 52. Okay, but from looking at the intensity ratio, this silver type of pig cannot be such cannot have such high weight percent. Okay, so weight fraction, so we have to refine the phase fraction. So select this phase fraction option, either of these two phase, and do the refinement again. Let's do the refinement again until it comes to a static value. Yes, now it is coming. See, this peak is intensity increases and this peak intensity gone down. Okay, and now uh, do the refinement for select this phase fraction checkbox and refine the instrument parameters once again. Go to the instrument parameter and refinement first three, then Gaussian coefficients, once again because it is going down. Yes, 8.3 we have achieved, so it's fair enough. Then do the XYG refinement. Yeah, it is still going down, so once again it's now 7.669. Check. Goodness of fit is 5.76 and weight residual is 7.669. So it is now looking all right, but still we can refine it further. Okay, but see the impurity phase, what I have told you, that silver phase, impurity silver phase we have not incorporated. So along with these two already incorporated phase, now take the silver in account. Okay, so import the phase for silver only. So silver sheep I am taking. Okay, and what we have found here, earlier we found that this value matching at 4.17. So I am manually doing that 4.17. Okay, so this is only silver. Okay, silver. Now check whether this page is here or not. Yes, silver. See, this cyan color one is for silver. This blue is for alloy having silver type unit cell, and this red is for uh, alloy having nickel type of crystal structure. Okay, so silver is now here. So it is actually coming, but we have to do the fraction refinement. Okay, so the phase fraction for silver is coming like 1.3%. So let refine that and check whether it has improved or not. Yes, it has improved now. Okay, so uh, after doing the phase fraction refinement, go to the instrument parameter refinement once again and do the instrument parameter refinement now. Okay. So following this refinement cycle, one again and again, one can achieve much lower weight residual value as well as the goodness of feed value. Okay, see the goodness of feed we have achieved 5.28 while the RW is 7.03. Okay, so I'm not going further, but from here I wanted to tell you that these XRD pattern actually have three phases. Okay, those are overlapped, although two phases are overlapped overlapped and one phase is impurity phase, that is silver phase. Okay, so from Rietveld refinement you can actually deconvolute this overlapped phase. Okay, so we have deconvoluted two different crystal structure of same alloy using Rietveld refinement. Okay, and after getting the good value and convincible RW and goodness of feed value, you can export the crystal information file from export option, then in entire project as full shape, and take the full shape like silver nickel alloy. Okay, then save it. It will you have to